To get cross-section, we have to take the square of the absolute magnitude of this guy, then various interference diagrams contribute. The first two, these are the familiar Parton model diagram, that's twist 2. Okay, twist 2 means power unsuppressed. And the Professor Sofa's lectures, and he focused on this contribution. In addition to these diagrams also contribute. Okay, here, okay, this lower block represents Coulomb correlation function in the nucleon. This doesn't have probability interpretation, unlike Parton densities here. And here, the 3 gluon correlation function contributes. For the single spin asymmetry, this diagram simply don't contribute. Therefore, these become leading contribution. Even though since this is twist 3, it is suppressed. Suppressed means it is order of 1 GeV divided by some large scale. But that large scale, if that large scale is in the region of a few GeV, it's not completely small, but this is also leading. In the second part of my talk, I will focus on this contribution. In the third part of my talk, I will focus on this contribution. So let's proceed. The first thing I want to discuss is the twist 3 analysis for single spin asymmetry at RIC based on the Coulomb correlation. This part is based on the collaboration with my former student Kanazawa, who is now in Temple University in Philadelphia. Before discussing the single spin asymmetry, let me make a brief comment on the unpolarized cross-section. This is the next leading order calculation for the pion production data comparing the experiment. And this is also the same thing. As these diagrams show, the next leading order pathological calculation, the collinear factorization, works perfectly well for describing the unpolarized cross-section. Therefore, it certainly makes sense to analyze the same data of single spin asymmetry by the same framework. Therefore, at RIC energy and also the future EIC energy, those data provides us with a good opportunity to understand single spin asymmetry in terms of the twist 3 mechanism I'm discussing. Okay, let's proceed to the single spin asymmetry. As I said at the beginning, this kind of Coulomb correlation function becomes necessary. Okay? This is defined as a light-cone Fourier transform of a quark field, gluon field strength, and quark field in the nucleon. And the Lorentz tensor decomposition defines 2 independent functions. Okay, by the way, gauge link operator is suppressed for simplicity. And by the P and T invariance, these 2 functions have these symmetry properties. Here, I just defined the gauge invariant correlation function in the nucleon, but whether the cross-section can be really expressed in terms of these functions is a separate issue, which we'll have to prove for each process. But in fact, we have shown that the twist 3 contribution to single spin asymmetry can be expressed in terms of this complete set of the Coulomb correlation functions. Yeah, we have shown the factorization property and the gauge invariance. Then let's proceed to the calculation of the hard cross-section. As I said, we have to analyze this kind of Feynman diagrams to get the platonic hard cross-section corresponding to this Coulomb correlation functions. As I said, for single spin asymmetry, it occurs from the interference between the amplitudes which have different complex phases. That complex phase is provided as an internal, the pole part of the internal propagator, namely here. Okay? By the I epsilon prescription, it gives rise to the imaginary part. And this pole, if we take the pole part from this internal propagator, it sets the x1 equal to x2. Namely, since x1 and x2 correspond to the momentum fraction shown like this, if x1 is equal to x0, x2, then this gluon momentum becomes 0. That's why this kind of pole is called soft gluon pole, and it gives rise to the contribution of this function. The another pole is also possible. If we pick up the pole part of this propagator, it sets the x1 equal to 0, and it gives rise to soft fermion pole contribution. Okay? By taking into account all these pole contributions, we eventually get the complete cross-section formula, which comes from this gluon correlation functions. Okay? These authors already derived the soft gluon pole cross-sections. And a few years later, we completed the cross-section by deriving the cross-section for the soft fermion pole contributions. And recently, my student performed a numerical fitting of the RIP data. The fold functions are parameterized by 13 parameters. The analyzed data points are about 61. And the result of the fitting is like this. In the negative XF region, although I didn't show, it's consistent with 0. For all pion and kaon, the result is the data is pretty well reproduced. And in particular, the previous analysis with the soft gluon pole alone couldn't reproduce the kaon data, but by the combination of the two effects, we could describe the kaon data as well. This is the result for the PT dependence. Although this is not included in the fitting, eventually the PT dependence is also well reproduced by the fitting. Next is the prediction. By using the obtained parameterization with the kaon and pion data, we calculated the cross asymmetry for the eta production. And this is the product prediction before the experiment was done. According to the calculation, the asymmetry for eta is twice as large as pi naught. And this is the experimental data appeared later. The data is approximately shows a similar tendency as the theory calculation. Namely, the asymmetry for eta looks larger than the pi unit. Okay. The reason for the asymmetry for eta is larger than pi naught is the following. It is due to the strangeness gluon correlation function in the polarized proton, and also the larger strangeness component in the eta fragmentation function. Okay. And this strangeness gluon correlation was responsible to reproduce kaon data, and that's also responsible for eta data. But there's one caveat. Although we included all the effects from the gluon correlation function, still 3 gluon correlation function and also the twist-3 fragmentation function effect are missing. So for complete analysis, we have to include those effects as well. Okay, let me proceed to discuss the 3 gluon correlation functions. Okay, as everybody knows, gluons are ample in the nucleon. About 50% of proton momentum is carried by gluon. Therefore, it's natural to expect that gluon correlation also plays an important role. Okay, so let's, as in the case of group correlation, let's first define the three group correlation functions. It is again as a light-cone Fourier transform of the three gluon field in the nucleus. Depending on how the color indices are contracted, we can define two kinds of two variable correlation functions, which I call O and N. Okay, let's skip the detail. Okay, because heavy co-production is dominated by gluon fusion process. Therefore, in order to study the pure gluonic contribution to the single spin asymmetry, the single spin asymmetry in the heavy co-production is very useful. So we studied this process. Okay, this is the diagram for unpolarized B meson production. Okay, this is the hard scattering part, and this green block represents B meson fragmentation function. Okay, the gluon density from two nucleons come into play. Okay, the result is it takes the usual convolution formula with the fragmentation function and two gluon densities and platonic half process. Okay, I finished. So. For the single spin asymmetry, we need to analyze diagram with the extra coherent gluon lines coming out of this. And these diagrams contribute, but that can be done, and eventually it takes this kind of form. Okay, unpolarized gluon density from an unpolarized nucleon, D meson fragmentation, and purely gluonic three gluon correlation functions from polarized nucleon. Okay, delta A is 1 for D meson and -1 for D meson. Therefore, if two functions have similar magnitude and the same sign, then it gives big asymmetry for D meson, but zero asymmetry for D bar meson. If O and N has opposite sign, then the result reverses. This is an example calculation, because we don't have any information about three gluon correlation function at this stage. We just saw what kind of asymmetry is caused by some choice of some model of the three gluon correlation function. We first chose O is equal to -n, and we chose two models. This G is the unpolarized gluon density. Maybe this is the preliminary big data for this is presumably upper bound of the three gluon correlation. As you can see, the result depends strongly. Okay, I'll come to soon. Strongly on the form of, in particular, the small x behavior of the three gluon correlation functions. Okay, let me summarize. Okay, we first discussed the RIC A sub n data in terms of the three co-gluon correlation function. The fitting of the star and Ramus data reproduce A sub n of I and k by the combination of the two contributions, and this analysis also reproduced the observed peculiar pattern of the PD dependence of A sub n pi naught. And our prediction for eta is approximately consistent with the star data. The origin of this relation is the strangeness content in the eta fragmentation function in the strange gluon correlation in the nucleus. For the three gluon correlation part, And we have derived the complete leading order twist-free cross-section formula for these processes. Although I didn't have time to discuss detail. And the important thing is that 3-gluon correlation function causes the A sub n for direct gamma production in the positive XF region. This is model independent. Therefore, if we find some positive signal in the positive XF region, it is totally governed by the gluon correlation function. And on the other hand, if we find some asymmetry in the negative XF region, it certainly comes from the 3-gluon correlation function. Therefore, it gives some constraint on the 3-gluon correlation function. That's all. Thank you.
We explain this twist-free contribution described by this quark-gluon correlation function and the 3-gluon correlation functions. But it is not clear that why do you don't include this twist-free contribution generated by this quark-quark correlation function. Twist-free contribution generated by quark-quark correlation function. Just this two fermion, two quark field. It also generates twist-free contribution. Two quark field, two non-local, two logical separated quark fields.
Two quark fields.
Yes, it also generated twist-free contribution, and they didn't include it, it seems to me.
You mean twist-free quark distribution?
Yes.
So it simply doesn't contribute.
Why? Because according to equation motion, they are related to this twist-free distribution.
It simply can't cause any phase necessary for single spin asymmetry.
But because you know, according to equation motion, these are correlated to this quark-gluon correlation. Because this operator, if you use equation motion, this quark-gluon operator is related to this twist-free quark operators. It is a bit, I don't quite understand about this point, because you can derive certain equation motions for these two operators. They are not completely.
Are you talking about the TMD twisted quark distribution?
Yes, yes.
TMD, that's separated. Okay, as I said, okay, that's suited for the description of the small PT single spin asymmetry. I'm talking about the single spin asymmetry, the large region, large PT region.
But the operators are the same.
Okay. Let me explain this. If the Koike's calculation is gauge invariant, then his definition has included the twist-free contribution from the two-part PDF, which generated by part of KT. That has been included into his definition. If his definition is gauge invariant, yeah. Yes. Unless you change the spin projector, but that part is not contributed. Okay. So.
Okay. Well, we can stop at this.
I think we can discuss this after.
Okay. Yeah. You mentioned this three-gluon correlation function, and you use some more. No, I talk about the second question. You use a model for this three-gluon correlation functions. I wonder whether you can derive this asymptotic behavior in QCD. You use the models in the second part of your talk. This
asymptotic behavior of what?
Of the three-gluon distributions. Because in some cases we know we can derive some asymptotic behavior of this non-polypeptide function in QCD. Whether we can work out it in this case or not. What's the reason?
In which region are you talking about asymptotic? What do you mean by asymptotic?
Because in the large Alice limit, in the large Q limit, because for the similar quantity will be distributed. You know, for if the unit scale is infinite large, you can determine the asymptotic behavior of the distribution. In your case, which is just the shape function, so I wonder whether you can determine this asymptotic behavior of this non-polypeptide function, like correlation function, which is precisely the correlation, the shape function, like for B methods.
I think it's beyond the scope of his talk. Okay, I think we have to change to the next speaker. So that's the second question. Okay, the next speaker is Professor Wakamatsu.
kind of invitation to this workshop, especially to Taiwan. I'm sorry to say in advance, but my talk has also a little to do with your standard modular physics, pure QCD talk. Let me talk about recent controversies of the neutron spin decomposition program and its possible resolution. Okay. So after 10 years of theoretical and experimental effort, we now believe that only about 1/3 of the neutron spin comes from intrinsic quark spin. So particularly the remaining 2/3 of the neutron spin. That is one of the fundamental questions of QCD. And especially delicate question is total gluon angular momentum can be decomposed into intrinsic spin part and orbital part in a gauge invariant way. To answer the above question without ambiguity, we cannot avoid to clarify the following question. What is the precise definition of each term of the decomposition? And how can we extract individual term by means of direct measurement? These are the core of the neutron spin decomposition program. There have been two popular decompositions of the neutron spin. One is Jhongli, and the other is G. And in these two decompositions, only the quark spin part are common, and other parts are totally different. And disadvantage of the Jhongli decomposition is each term is not separately gauge invariant, except for this quark spin part. On the other hand, each term of G decomposition is manifestly gauge invariant. But it is claimed that this total gluon spin part cannot be gauge invariantly decomposed into intrinsic spin and orbital parts. So first pay attention to the difference between the quark OAM and two decomposition. What appears in the G decomposition is a so-called canonical OAM, X cross P, which is not gauge invariant, of course. On the other hand, what appears in the G decomposition is a mechanical OAM, X cross P minus GA, which is manifestly gauge invariant. So gauge principle dictates that the observable must be gauge invariant. So by this reason, the observability of the canonical OAM has long been questioned. And on the other hand, it has been shown that the mechanical OAM can be related to observable through GPT. This is its finding. However, several years ago, Chung-Yuan, Goldman, et al. Proposed a new gauge invariant decomposition. The basic idea is decomposition of the total gluon field into the physical component and the pure gauge component, which is a sort of generalization of the decomposition of photon field in QED to transverse component and the longitudinal component. Their decomposition is given the following form. And the prominent feature of this decomposition is each term is separately gauge invariant. And it reduced to gauge variant Jhongli decomposition in a particular gauge. And soon after, we noticed that the way of gauge invariant decomposition is not necessarily unique, and proposed another decomposition. The feature of this decomposition is as follows. The first, the quark spin and gluon spin part are nothing different from chain decomposition. But quark OAM part is just coincide with the G decomposition. As a consequence, the gluon OAM part is also different. It consists of two parts. One is the canonical OAM part, and the other is the term which we call the potential angular momentum term, because the QED correspondent of this term is nothing but the orbital angular momentum carried by the electromagnetic potential, which appears in the famous Feynman paradox of classical electrodynamics. And the arbitrariness of the spin decomposition arises because this term is solely gauge invariant. So shifting this from the gluon OAM part to the quark OAM part, we just obtain the quark and gluon OAM part, term in the chain decomposition. Further, we found that we can make a seemingly covariant extension of the two gauge invariant decomposition of QCD angular momentum tensor. And we called it the decomposition 1 and decomposition 2. Remark is order. The word seemingly is important here because the following decomposition, which is a foundation of the above decomposition, is intrinsically non-covariant or frame dependent, as we shall see. Still, it is useful to find the relation to hierarchy DIS observable. It is also useful for productive calculation of Feynman diagrams. And we start with decomposition 2, which is a seemingly covariant generalization of chain decomposition. And characteristic feature of the decomposition is the quark OAM part and the gluon OAM part both contains a pure gauge covariant derivative, in which the gluon field is replaced by a pure gauge component. And remark is this decomposition reduced to any one of Bashinsky-Jaffe decomposition or chain decomposition and Jaffe-Manoa after appropriate gauge fixing in a suitable Lorentz frame. And this decomposition may be called the canonical family. And another decomposition, 1, is in a sense extension of G decomposition. The quark OAM part contains just full covariant derivative. Accordingly, the gluon OAM part consists of 2 parts, canonical part and the covariant generalization of potential OAM part. And this decomposition may be called mechanical family. And our claim is that basically there are only 2 physically non-equivalent gauge invariant decomposition 1 and 2 of the nucleon spin. Decomposition 1 contains G decomposition. Also, JG can be decomposed into 2 parts. And decomposition 2 contains 3 of popular decomposition, Bashinsky, Jaffe, Chen, and Jaffe-Manoa. However, the opposing claim has rapidly spread over the QCD spin physics community because the decomposition of the gauge field into its physical and pure gauge component is not unique at all. There are infinitely many such decompositions. Therefore, there are in principle infinitely many gauge invariant decomposition of the nucleon spin. The argument in favor of this claim is due to G and his collaborator. According to them, the chain decomposition is a gauge invariant extension of the Jaffe-Manoa decomposition based on a Coulomb gauge. On the other hand, the Bashinsky-Jaffe decomposition is a gauge invariant extension of the Jaffe-Manoa decomposition based on a Lycomb gauge.